But anyways, let's get started here. Let's just talk a little bit about the exam. I think everybody did pretty well, all things considered. The average uncurved was about a C, or it was a C. It was kind of a low C, which is pretty good for an engineering class, all things considered. I did decide to curve it a little bit, so I went from a low C to a high C. So it was around 74, 75 to about 76, 77 after I curved it. You should have gotten 2 points. I put up an announcement. If you haven't looked already, I would suggest you go look at it. It was just a list of questions, and there were some issues with drop downs, specifically if there's only one drop down on a question. For some reason, it didn't work. And then there was also maybe one or two questions that we didn't cover. I think there was only one, and I wanted to cover it anyways here. And that was for half credit, so I wanted to give that. Did anybody have any specific questions that they wanted to go over from the exam that they had? And if you do, preferably if you could give me the number with the parentheses around it, not just the question that you had, since there's going to be a difference between everybody's questions since they are randomized. I guess in the meantime, if anybody does have those questions, we can go over a few that I screenshotted that I wanted to talk about. So I got a new whiteboard application over the weekend as well because the other one was kind of lagging. So hopefully this one's a little bit nicer. It seems like the images are easier to use, so that's good. But I screenshotted a few questions and I just wanted to go over them first before we get back into talking about stuff. Actually, before we do that, one other thing, just to note, is the exam average was about a 75 before curving. So that was for the exam, and then one thing I did want to note was that a lot of other sections I think are doing extra credit assignments, so I wanted to give one as well. I don't know exactly when I'll have that done, but I'll probably have the due date be about a month and just give you guys quite a bit of time on it and just have it be something comprehensive. So there'll be some kind of extra credit assignment probably. I'll let you know when I have something picked. I just want to ask, would you all rather do something that's more design oriented or more math oriented if I was to give another extra credit assignment? Math related? Okay. Fair. Any other inputs from anybody? Math? Okay, fair enough. And I might put something up on Canvas as well. But okay, fair enough. We could do something math related. And then I'll let you guys know when I come up with something for that. I'll just have to think about it a little bit, I guess. Okay, design. That's fair enough. Maybe I'll do a little bit of both. I just wasn't sure how everybody felt about math, if anything, just because I know some people hate doing it in courses like this and some people like it, so maybe just a little bit of both, then I guess. Right, so I'll let you guys know, I guess, when we have that. The other thing was, I know I mentioned maybe like a week or two ago that I got a request from a student to do a stream of one of the assignments because, maybe it's helpful to work through those and kind of see how you might program it if it was to kind of look cleaned up. And I think I should have time this weekend, so I wanted to do an assignment 3 stream, was specifically the one I got asked to do. And normally I like to do these with early on assignments. I just didn't have a whole lot of time this semester. Assignment 3 stream via WebEx. I'll send a link. It'll probably be Saturday. and I'll ask what time works best for everybody. My plan was 1 p.m., but if there's a time that works better for everybody else, maybe we'll change that. But just as a heads up, I'll be working through assignment 3 and just kind of being able to see, how I might solve something like that, I guess, and clean up some of the code just for reference. And I will post the code afterwards as well, just so that everybody can see it. So I think that's everything administrative related. I did want to go back to these questions. So this was a one that a lot of students missed, and the first version of this question I think is a little bit ambiguous out of context if you don't have both of these. So I tried to be kind of lax with grading on those, especially if there were a few questions that I thought the wording was a little vague, and I tried to be nice when grading those ones, and this was one of them. So we have these two questions, and really the only difference between them is that part. So this one has the new int and that one doesn't. But the question is, for the following declaration, explain which section of memory is allocated and whether the program needs to free the memory. And so between these two, we have just an integer pointer and an integer pointer equals new int. And so I got a lot of answers that this one does an allocation. So I think this one is the harder one, which is technically not wrong, but I guess not really what we were looking for on that one. But this one definitely does do an allocation. So when they're asking for allocations, they're specifically referring to when you use the word new. That's the keyword there. There are some allocations that are done behind the scenes whenever you create a variable, no matter what. That's just going to be something that happens that you can't really stop. But an explicit allocation that you have control over, the first one you have, if assuming that's only things that you have control over, the first one, there is no allocation because this is just a pointer. So you make a pointer and it points to nowhere. It probably points to some location, but there's just garbage there. And there's no memory allocated at that space. But when you use the new keyword, then it's going to create an integer. How many ever bytes, 4 bytes that is, and then return a pointer to it. So this one is going to do an allocation and keep the pointer to that allocation, whereas this one is just going to make a pointer and the pointer is not pointing anywhere until we actually do something that gives it something to point to. So that's the difference between these two questions. I think more people did get this one, which I think was more difficult out of context. And then, so the second part of this, does the programmer need to free it? Well, if there is no allocation, then you don't need to free it, so this one's a no. And this one, since there is an allocation, even though it's an integer, which is pretty small, that's still memory that we could be freeing. And so, yes, we would want to free this integer. And when they say free, that's, I guess, interchangeable with the word delete. I wanted to clarify as well. In C++, they use the word delete, which is what we're probably used to. If you're used to C, which C++ does support, then you can use the word free instead of delete. It's a function call rather than just a keyword, but you can use that to free memory as well. So those are interchangeable, just for the future to keep in mind. I think we briefly mentioned free. I don't think I talked about the C version of new, but I guess just offhand, the C version of new is called malloc, and it stands for memory allocation. And, well, I forget the syntax, but I think it's just malloc and then a number of bytes. So if I wanted to do an integer, I might do something like that, or probably something more like this, where we do size of an integer, and this will allocate an integer. It's a function call, and it takes a number of bytes to be able to allocate that thing. And it's exactly the same as if we did the new int blank. Then this is equivalent to that, but this is the C version of it. So if you ever write C, this is what you have to do in place of the new keyword. And personally, I kind of like this one better. I think it's more readable in terms of programming, but just something to be aware of, I guess, because C and C++ use different words sometimes. Right, so the other question, I think there are two more, is describe what it means for a class member to be static. And I got a lot of the same answer, and I think it was just the way I worded it when we were going over it in lecture. I maybe put a little bit too much emphasis on an aspect of it rather than the definition of it. So the answer I got pretty frequently on this one was it's something that exists one time, which, while true, is not the definition of static. So if something is static, remember that we usually have done that in the context of classes. So if I had a static thing for, let's just say, a person class, then we have instances of that person that may have their own names and ages and attributes and stuff like that. And we might have things that are static, like, for instance, a count. It keeps track of how many people there are, but that's not attributed to any single person in my collection of people. And so static variables, the definition of that is just it's independent of any instances. It doesn't belong to an instance, but the answer I got pretty frequently was just that it exists one time, which, while true, isn't necessarily the definition. Although I did give more points for that one because that was somewhat my fault. I think I stressed that kind of not well when we were doing the lecture. But just so for clarification, it just means that it's independent of an instance. It doesn't belong to an instance. And so that could mean that it's a static member, like here, which is actually what the question is asking for. But it could also mean things that are just static in general, like global variables, which don't belong to any class and do exist one time, but they're just independent of class instances. Just a clarification on that one. And then the last one, which was on that list of ones to give back points for, I was going to give back half points on this one because I didn't cover the second point of it, which this question gives a block of code, and it says the new operator is used to dynamically allocate memory, and to avoid memory leaks, what changes can you make? Just for the answer to that one, well, that one's not too bad. It's just throw a delete in there. So they allocate a array, and then they populate the array. So this one should just be delete with the braces pointer, and that's all you need for this one. But that's fine. I think most people got that anyways. The part here that I wanted to go over, because I didn't cover it, although you did kind of use it, was write the command to check memory leaks. And that's been on code grade, but I never explicitly mentioned it, so that's why I want to give back points on that one. It's called valgrind, and you just use it, and then some amount of flags you can do, like memory leak. I forget exactly what all the names are, but memory leaks equals 1 or something like that. If you go to code grade, you should see a full run on it on both assignment 4 and assignment 5. And then the name of the program or command that you want to run, so like /a.out. And this will just run your program and then check if there's a memory leak when the program ends, either that you didn't deallocate something before main ended, it checks for that, and then it also checks for any actual like serious memory leaks that you had that you just maybe didn't actually deallocate. So you can use this for testing in assignment 5 as well if you want. It will auto test it for you in code grade, but that's what that means, and if you ever need to use it, that's the command. Cool. So before we move on, any last questions on the exam that anybody wanted to cover? And for those of you who came in late, I do suggest checking to make sure that I gave you 2 fudge points. So I gave everybody a constant curve of 2 points. There's a thing on Canvas that says like fudge points at the bottom, and everybody should have gotten 2. And also there's an announcement on Canvas with all the questions that you should have gotten at least some points back on because there was mistakes. So please look at that and make sure if you got any of those questions that it did give you points back. Okay, fair enough. I don't see any questions, but if you have any, just feel free to stop me. Okay, cool. So we can go back to talking about stuff that we were talking about maybe about a week ago, probably a little longer. And we were done with programming stuff, which is great. We were done with all the programming structures that C++ has to offer. We were kind of just all looking at conceptual stuff for the rest of the semester, which I think is nice just because it's less rigid. We can actually kind of think through this a little bit more. We started talking a little bit about recursion, I think 2 weeks ago at this point, and we did an example of factorial, and so let's think about that again. I think there's a way to make grids on this, which is nice. Maybe I'm going to make it slightly different. So I want to end. I hope I haven't messed this up. I was hoping to make this a little smaller, but oh well. That's totally fine. Let's just go ahead and work through this. Can I move it with this? Nope. Alright, well, one of the rows is just going to be bigger. Oh well. But we started talking a little bit about recursion in the context of factorial. So what I'm going to do here is just write out n being some counting number that's, you know, a natural number, and then some expansion of n factorial, and then actually let's just do it this way. I can move this a little bit. Okay, there we go. So we'll do n factorial, and then we'll do the expansion of n factorial. So let's just do it with a few counting numbers here, and I'm going to go in reverse order. Let's start at the number 3, 2, 1, and 0. So we want to find what 3 factorial is, 2 factorial is, 1 factorial, and 0 factorial. I think it's probably better to start with these ones. So remember that a factorial just means you multiply by a number until it reaches 1. So this would be equal to 3 times 2 times 1. This would be equal to 2 times 1. This would be equal to just 1 because 1 is the only number there. And then 0 factorial can't really do that because you can't count down from 0 to 1 because it's lower than 1. So this is just 1 by definition. And so if you remember last week, what we said is that we can kind of rewrite these so that they're in terms of things that come before them. So we notice here, this 3 is tacked on to the 2 times 1, which is what 2 factorial is. So 3, in some way, we could write it as 3 times 2 factorial, because if we just kind of chop everything off other than the starting number, that's what that is. And then we can write 2 factorial as 2 times 1 factorial. Since 1 factorial is just 1, we could kind of plug that in. And 1 factorial is just equal to 1, again, by some sort of definition. Or there's not necessarily definition, but it's just, we can't go any further. It's a stopping point. And so we have the ability to rewrite any of these then as whatever the current number is. So this one was like 3 times 2 factorial, which is the number lower than 3. And this one was 2 times 1 factorial, which is the number that's 1 less than 2. So we're able to write these in such a way that we take whatever number n it is that we're taking the factorial of, and we multiply it by the factorial of the number 1 lower than it, n minus 1. And that works for both of these, and it even works for 1 if we really wanted to make it work. But it definitely doesn't work for 0, for sure, because 0, there is no n minus 1 factorial. Negative 1 factorial doesn't equal anything, at least not by any standard definition. So there's no way to define it by this. And so it kind of breaks the mold. It's the one of the two exceptions I'm going to say to our pattern here. And so rather than being able to write this as some sort of function like the above one where we can write it as an explicit formula, then this is something that we kind of have to address if we're going to program it, because we can't, or not, sorry, not base, class base case. It's something that we can't write in terms of anything else. And I'm going to argue that we do the same thing with 1 as well. Let's just say that's a base case. We can't write it in terms of anything else. It's a fundamental, like atomic unit, can't be broken down into any further function calls. And I think what we started to do was we started to say, okay, well, we can write this as a function then. And so if I have a function called factorial that's integer returning, let's just say, and takes some integer n, then we had the ability to go and return the value of n times the factorial of n minus 1, since that's what it equals by definition. And so this excludes our base cases, but it at least covers every number that's greater than 2, greater than or equal to 2. Cool. So does anybody remember what the issue with only covering this would be? So say I exclude those base cases and don't do the definitions, because maybe they're just special cases and I don't necessarily have to do them. Do I still have an issue with what I've written? Or does this at least calculate all the numbers 2 and bigger correctly? Right, yeah, so we get an infinite loop. You're exactly right. Because if I was to call this with 2, let's just say, then it would plug in 2 for n, it would plug in 2 minus 1, which is 1 for factorial, it would go back up here, call it with 1, we would get n equals 1, it would plug in 1 for n, do 1 minus 1, which is 0, go up and call factorial again, make this 0, make that 0, and you see that we basically go past 0, which is one of our base cases, and 1, which is one of our base cases, and we're just going to infinitely loop until the program crashes, because it's going to run out of memory because it's doing too many function calls, which is stack overflow. Right, so you're right, that's an infinite loop. This would crash our program. One convenient thing, I guess, about recursion when we're doing this is you can generate infinite loops, but you'll at least have an idea that you did so, because it will crash, unlike a while loop. But because of that, we actually have to do the base cases, and those act as our stopping points. So we said that if n is 0 or n is 1, then those are our 2 base cases, and we can return 1, since that's what they are by definition. Something important that will 100% be on the exam, I can say with confidence. Oh, whenever this stops lagging. You can have as many base cases as you want. You're guaranteed to have at least one base case because it acts as a stopping point for your code, but you don't have to have just one base case. And it's a point of confusion I've seen a lot. A lot of the examples we're going to do have exactly one base case, but that's not always the case. In this case, right, I was able to do 2 base cases technically because I had a base case of 1 and a base case of 0. Scroll seems to be just completely broken. I don't know why. Oh, what happened? There we go. We have like 2 base cases here, right? 1 factorial and 0 factorial. Whoa. Okay, I was going to say this program was better, and then it just started doing that. But we have 2 base cases here. I could do 1, but I could say 2 is a base case as well, and just say if n equals 2, return 2, and there's nothing stopping me from doing that. So you can have any number of base cases. Usually you want to do it with only how many ever are necessary. In this case, 0 at bare minimum is necessary, but that still doesn't mean that there's always going to be one base case. There could always be more if you're doing more complex problems. So just keep that in mind, and maybe the recursion homework will have something about that. I'm not too sure yet because I don't think it's been created. Okay, so let's go back to this one. Nope. Okay. Actually, let's go ahead and program this first. I've started a program here. It's not really going to do anything special. It's just going to do a bunch of recursive functions, but I kind of want to work through them here in class, and then I'll just post them. So let's just go ahead and program what we had. So we said we have base cases if n is 0 or n is 1. And we return 1. And then otherwise, we can return n times the factorial of n minus 1. Oh, I call it factorial. Factorial of n minus 1. And then just to see that that works, let's go ahead and print that. So we'll say the factorial of 7 Actually, it might be better to just do a smaller number. Let's say we do 5. I think 5 factorial is 120. Yeah, it should be. 6 times 20. So let's see if it works. Ah, and I don't have these other functions written yet, so it's not going to let me. Let's just write return true. Head version, tail version. Did I make a typo? Oh, right. C++ doesn't like when you put default arguments twice. Okay, cool. I think... Yep, there we go. Just like I said, when we do 5 factorial, it equals 120. So it seems to work. We'll call it with 5, and then call it with 4, and then call it with 3, and then call it with 2, and then call it with 1. So let's actually write that out just a little bit here. You can kind of expect some sort of tree when you do these kinds of calls. So when we just did factorial of 5, what this is essentially going to do is it's going to say that this is equal to the return value, which is factorial of, or sorry, 5 times 4 factorial. So that's going to do 5 times factorial of 4. And then this call is going to go do 4 times the factorial of 3. And then this is going to go do 3 times the factorial of 2. And then this one's going to go do 2 times factorial of 1. And then this one's going to evaluate to 1, right? So if you kind of do this out as a tree where every time you do a function call, you go and figure out what it is that it's going to evaluate to, eventually you're going to hit a bottom, which is our base case here. So when we do factorial of 1, that has a definition. It is a base case, and therefore it's going to return a value. And what you'll see happens when you actually do this, these are all the return values from each function call for this being the n number, then it's going to kind of propagate its way up. So it's going to return this to be 1, and then do 2 times 1, which is 2, and then return that here, make this 2, and do that times 3, and then return 6 for the function call here, and then you'll do 6 times 4, which is 24, and return that here, and do 24 times 5, which is 120. So if you kind of follow where your function calls go, you can get an idea of what the actual value is going to be, and it will just kind of work its way up this tree. Now it's not super interesting for this one, but we can kind of modify the way that this is called when we do other examples, and we'll see this with 2 examples that we've done later. But this is just kind of the general strategy for this, or general overview of what that looks like. And something to keep in mind, because I do think it's a point of confusion at first when people are learning recursion, is the fact that this will propagate up this tree. Whenever you finally reach something that is a stopping point, a base case, it's going to gradually return until it reaches back up at the top of this where your actual answer lies. So our initial question was, what is 5 times factorial of 4? And we can figure that out if we just evaluate everything lower than it. Cool, so that's what the factorial ends up looking like. Just generally, I guess, related to this, if we're talking about recursion when it comes to computer science, because that will probably be another thing that's on the exam, I imagine, it just means for a function to call itself. It's really that simple. When we're talking about it from a mathematical standpoint, it means something like this, where it is something that relies on a previous solution to the same problem. So 5 factorial is reliant on 4 factorial, which is a solution to the problem, and then 4 factorial is reliant on 3 factorial, and so on and so forth. And it doesn't always have to be necessarily going downwards. It could go in any direction, but we do have a way to have it be related to some other solution to the same problem, I guess. Actually, before we tackle the next problem, let's also talk about that code a little bit further. So there's 3 main things to consider when you write recursion. So there's 3 things that you absolutely always need. And one of them I've already written down, which is the base case. So a base case is always needed. This is our stopping point. The purpose of this is to stop the recursion from happening at some point, so we don't just recurse forever and crash our program. We need the recursion itself. Otherwise it wouldn't be recursion, so that one's kind of self-explanatory. And then there's actually one more aspect. So consider the base case is there to act as a stopping point, but we need to approach the base case and eventually reach it. Otherwise, we're never going to actually stop our program either. So there's an extra thing here, and in this case it's by subtraction, but it doesn't have to be by subtraction. And we're going to see in a lot of examples that we do that subtraction is going to be what we do, and that there's going to be one base case, but remember that that's not always the case when we do more complex problems. And this is what you might call a reduction operation. It's just what I'm generally going to call it. And again, be careful. The name reduction in English almost seems to imply that this means getting smaller, but that doesn't always necessarily happen to be the case. We could actually have addition be a reduction operator, and I'll maybe do an example of that later. But yeah, the name reduction operator can be a little misleading. The name reduction in general, I think, can be in computer science. But it means that it approaches a base case. So what this means here is that if we were to start with 5 factorial, when we do n minus 1, it's going to equal 4, and then when we do n minus 1 on that one, it'll equal 3, and then 2, and then 1, and then 0. And so the operation that we're doing, the subtraction, makes the numbers that we're using, or values, it doesn't have to be numbers, it could be something else, but it makes them approach our base case. In this case, it makes the number approach 0 and 1, which are our stopping points. So these are the 3 key points to recursion. You need the actual recursion itself, you need a way to approach a base case, and then the base case, which actually stops your program. So I wanted to do a few more examples. I wanted to do an example of going through an array. So I have an array already defined in the program, and it's just multiples of 3, so it's 3, 6, 9, 12, and 15. And what I want to do is write a quick recursive program or function that is able to tell if a number is in this array or not. And so if we were to write this explicitly the way that you have probably written this before for CS135, is you might do something like this where you say int, well, let's make it a function call. Let's say bool is found, and it takes the array, we'll just say of integers, and then it takes the number to check for, we'll just say n. And so if you wanted to check if n is in this array, what you might do is just do a for loop int I equals 0, I less than whatever the size of the array is. So I guess we would need to pass that as well. Let's just pretend I passed it. Let's say I less than size, I plus plus. And then we would check if r sub I equals n, then we return true. Else we don't return yet because we need to search through the entire array. And then if the whole for loop goes through and we don't find the thing that we're looking for, at that point we can return false because we didn't find the thing we're looking for. And so that's just a general linear search that you're probably used to for like 135. We just want to search this array and see if that's found in there. We can also do this with recursion. So something to note about recursion is that anything you can do with a loop, you can do with a recursion and vice versa. That doesn't mean that you should do things with recursion. In fact, it's usually slower, if not almost always slower, and consumes more resources, but sometimes it's easier to think through things recursively, as crazy as that may sound at first. So let's just say this takes the same arguments. We can do this recursively as well. Actually, on that note, never do the factorial the way I did it. Just program with a loop. Don't ever write it that way. It's just for an example. Something to keep in mind. It's actually like horribly inefficient to do it that way, but we're just learning. So keep that in mind. But what we're going to do is we're going to check through an array again if it contains a number n. And in this case, we actually need to keep track of something extra, which is we need to keep track of the index. We want it to be 0 by default, and then we'll kind of work our way through this. When you do something like that, you actually have to capture the starting point in your function call. So I'll write some more code off to the side here, but we need to know where we are in the array. So what I'm going to do here is I'm going to check if array sub index, we'll just say I, is equal to n. Then we know we found the object, return true, and then otherwise, actually, so I guess we should check one thing above that. Oh, that was kind of close. Okay, that's good enough. I'm going to check it up here and check if I equals size, return false. And this might not seem obvious at first, so let's explain it a little bit in more detail. So what this says is we enter the function. So there's an idea of like a precondition and a postcondition when you're programming anything with a loop or recursion, and they're not always well defined. They're just kind of things that you as a programmer need to figure out. So I want to talk about those a little bit. A precondition is something that you can assume is true when your function or loop starts. And so it's something that you can know for a fact is true when you go to execute your code. And the postcondition is essentially the same thing. It's just once your code is done executing, you can assume that that's always true as well. When you're doing loops, you generally want your precondition and your postcondition to be the same because you want it to be consistent. Because if you go into a loop, you should have some expectation that you're going to do it again. And because of that, the thing at the beginning of your loop and the thing at the end of your loop need to be the same goal, because the end and the beginning of a loop are essentially the same when you're hopping back up to the top. So I'm going to do these both as one single thing here. So I'll just say post condition is we are up to I no match has been found. So that's something that should keep true no matter how many times we call this function. And another thing that we probably want to note is just what this function needs to do, which is, I'm going to just say it needs to check, is the number n located at index I? So you can see these are kind of related. Our problem that we're trying to solve is that the number that we're looking for has not been found yet up to some index, which if you think about it is the same condition that we're trying to do in this loop here, right? If you go through this loop, each time you're checking, is my number at index I? And that's the problem that you're trying to solve. If it is at index I, then that's great, you've solved the problem, and if not, you need to check the rest of the array. And in the same way here, what we're going to try to solve here is at position I and before it, we have not found a match yet. So we want to check position I and everything after it, if needed, to see if we're going to actually find our thing. Oh, and I haven't finished writing this function. So the goal of this is, like you would do in the single loop, we need to check at position I, see if the thing is there. If it is, that's great, we return true, which is what this condition checks for. If not, we need to check the rest of the array. And then we have one extra thing here, which is our base case. So I'll just put a note here. This is our base case. We need to break out and say that we haven't found it if I is equal to size, because that would mean that there's nothing left in the array for us to check. And therefore, we can't do our goal anymore. Is the number located index I or later, I guess would be the extra part there. And since there's no index I or later when you've reached out of bounds of an array, that would break our condition, and thus it's false. But we do need to do something extra here, which is we need to consider the rest of our problem. So our problem is, if we found it at position I, then that's great. But if we haven't found it at position I, then we need to keep searching. So I can put an else, I'll just, I guess, not have it there. And what we need to do is then search the rest of the array, which would be our function call, which is called isFound. And we would pass it the array. We would pass it the n we're looking for. We would pass it the size, since that's consistent. And then we would pass it I plus 1, which is the next index. So if we consider what this is saying here, excluding the base case, which is just to stop our program, we're saying if we found the thing, then we found it, we can return true. Else, we need to search the rest of the array, which is the item in the array, so is the number n in the array of size, since we need that as an argument, for all of the indices that are at I plus 1 onwards. And so that line of thinking allows us to say, can we solve this in terms of a different kind of problem, which our problem here is, can we find the thing in a smaller array, being the array to the right of where we currently are. So let's actually draw that out in a little bit more detail, but this should be the code. It should work totally fine. So let's just say I have the array here, 3, 6, 9, 12, and 15, and 18. And this would be index 0, 1, 2, 3, oops, that's not an I equals 0 through 5. And then let's just consider our function calls as we go. So the first thing we would do here is we would call this with is found, the array, the number we want to check for, let's just say, I don't know, 12. Let's do it partway through. And then the size of the array, which is 6, and then 0 as a starting point. So what we're saying here is search through the array for the number 12 until you hit 6, and starting at the position 0. So if we kind of consider that, it's going to go here, and it's going to check the position 0, and it's going to say, is that 12? Well, it's not. And so we move onwards, and we say that I is then equal to 1. So for the next function call, we would end up having it in such a way that it would call the same function, right, with pretty much the same exact arguments. R, 12, 6, and then it would do 0 plus 1. Similar to what we have up here, where we take whatever the I was of the previous step and add 1 to it. And because of that, we end up saying, okay, well, now our condition is we haven't found it at position 0 or anywhere to the left of 0, which is nothing. Let's try to look for it in the array to the right of that, which is this stuff. So we're saying, starting at position 1, can we find anything else? So we go and we check there, and our function checks, is it located at position 1? Well, no, it's not. Then what we need to do is check the array to the right of that, which is all of this stuff here. And so you can see that it kind of shrinks down your problem gradually, where we start with an array of 6, and then on each call, we are reducing what we have to work with until we reach something that is more manageable and actually contains our solution, or it shrinks so small that we just can't do anything further. So we get to the I equals 2, we check if it equals the number that we're checking for. Does 9 equal 12? It doesn't. And so we say, check if 12 is in the array to the right of this. And so we add 1 to it and say, is it in the array with the index 1 bigger than 2 being 3? And we check this one, and we check the first position. Is 12 equal to 12? Well, yes, it is. And so this returns. So you can see it does the same exact procedure as if we did the for loop. It's just in a more abstract way, where we're saying, can I find this thing to the right of where I currently am, or is it currently in the position that I'm looking for? So it's more of boiling it down to the kind of problem that you're solving, rather than thinking about it just kind of straightforward. And just for the sake of our example, if I was to call this with the number 20 instead, let's just say, or n equals 20, then it would keep checking. It would check if does this position work. We'll go to there. Does this position work? Is that one 20? It doesn't. And then it would check there, and then it would say, well, it doesn't find there, and so it goes out of bounds to 6, which is also the size, and at that point we have an array of just nothing. And that's kind of our base case here, is if we were to try to ask the same question again, can I find the number 20 in the array to the right of 6? Then no, I can't, because there is no array to the right of 6. So our base case for a problem like this is, can I find this number in an array that contains nothing? And your answer to that is always no. You can never find a number in an array that contains nothing, because, well, it contains nothing. So that's kind of our problem that we've solved up here. If I is equal to size, in other words, if we have a completely empty array with nothing in it left to search, then it's impossible for us to find the item, and therefore that's our base case. That's when we can return false. If the item that we're looking for is there at the position that we're checking, that's great. We can return true. Otherwise, return the result of checking the array to the right of the current array that we have, or the current index that we're checking. Does that kind of make sense? Or any questions on that? I know this is very abstract, and so it might be hard to wrap your head around at first. But that's just the general kind of problem solving for stuff like this. Okay, if you have any questions, please feel free to stop me. I'm just gonna write the code for this really quick. And I'll comment this more in detail before I put it on canvas. So we need the elements, we need the size since it's an array, and then we need the index that we're checking for. I'll call it index just so it's a little more clear in the code. So what we need to do is we need to check if index is greater than or equal to size. Equal should be fine too, but I'm just going to put greater than or equal to size, then return false. If we find the thing, we can return true. I called it element here. And then else we want to return the result of checking the array with all the same parameters, but starting at index plus 1. So let's just make sure that works really quick. We'll say is 12 in the array. What did I call it? Is element in array. Oh, I need to actually change the arguments. For convenience, I'm going to make this index equal to 0 to start with. Excuse me. And we'll pass in the array we have. It is 12 that we want to check for. Array size 6. Let's just throw that there, throw that there, and then we don't need the last argument because I wrote it in such a way that that's not necessary. And then we'll check, like we did in the example, is 20 in the array. I think that's all we need. Let's go ahead and run that, see if it works. And we see with no end line, but is 12 in the array 1, which is the boolean for true. So yep, 12's in the array, and is 20 in the array 0, which means that it's not. So it seems to work. Okay, so let's do one last function really quick that is going to print a string backwards. Actually, sorry, one last note about this. I did mention earlier, this program's a little laggy. It'll get there eventually. It's faster to do it via the program. Right. What I was going to say was, we mentioned earlier that the term reduction operator can be a little bit misleading if you just use the standard English definition and like try to apply it to math operations, at least directly without thinking about it more. And subtraction is usually considered something that reduces things, but the thing that actually did our reduction in this problem was adding 1. And so our reduction operator in this case was plus, and plus 1 specifically. And so just keep in mind, reduction doesn't always have to mean subtraction. the reduction in this case was the reduction of the size of the array left to search, rather than a reduction in any kind of number. So just be careful with that kind of definition. Reduction doesn't always necessarily mean subtraction. And it doesn't even have to mean reducing the size of something either. It just means that it has to approach our base case. As we'll see when we get to recursive lists in maybe like a week or so. Okay, so that's our searching through an array. Let's go ahead and just do an example of trying to print a string backwards. Let's say I have some string. Let's just call it str. And what I want to do here is just print it backwards. So I want to say that there's two common approaches that we could do for this. We could either go backwards. So I think this is the way I would think to do it if you just asked me without thinking about recursion. I would say let's start at the last letter and then just work our way back and kind of add to it. And then there's another way where we could go to the forward part and kind of append what we have already. So let's just write these two the standard way that we write them. I have something called finish string. We'll let it be that. And then we could loop for int I equals 0, I less than the string length. I think you can just call str.length in C++. I++. And then what we could do is we could just add straight to the string and not do anything special and just say that the finished string, we can add each character plus equals our string sub I, and I need to start, sorry, I did this backwards. We would be starting at the end and working our way to the front, right? So my indices are out of order. Also, I should probably write that before somebody tells me it's a syntax error. Okay, so we have that. If we wanted to go backwards, like start here and work our way to the back, then we would need our first index here to be the length, and then the second part to be greater than or equal to 0. And then this would need to be I minus minus, I guess, as well. So it would equal to str.length minus 1, and then we would say while I is greater than or equal to 0, I minus minus. So we just start at whatever the end index is, and then subtract until we reach equal to 0, which is our last one, and then kind of add it. And so this would add O first, and then L, and then L, and then E, and then H, right? And it would always add something to the end of the string. So it would start with O, and then the next letter that comes after that goes to the right-hand side of what we have already. So this was what we started with, was just the O, and then we have OL, and we add an L to that, and then with the OLL that we have, we add an E and then an H afterwards. So we add things starting at the left side, and it grows going in the right direction, which I think is common sense way to do it, at least in my opinion, is to make it grow right, at least if you're doing it this way. That's the way I would think to do it. The other way we could do this is we could write it in such a way. So let's say we have those same two variables. We'll say we have str, I want it to be black, str equals hello. And then we have some sort of finish string. That we initialize to nothing, and then slowly build on top of it. So I could do another loop where I go in the forward direction, but instead of adding the thing to the right side of my completed string, I add it to the left side. So for this one, we could say, I'm just going to shortcut this if you don't mind. For I equals 0 to the length minus 1. It's actually to length, I guess, because it's exclusive. I++. I am writing pseudocode, so this wouldn't actually work in C++. And this whiteboard doesn't seem to like it. Oh well. So we can say we could iterate through I equals 0 to length, and then instead of just adding each character to the right hand side by going backwards, what we could do is we could take the current string that we have and add the next character to the left hand side of it. So we could say str sub I plus the previous finished string. Doesn't fit on screen, that's okay. And so this what would do if it would stop lagging. Oh, I'll just write it up here. What this does is it starts with the letter H, and then it's going to add the next character, which is the letter E, to the left. So it'll take whatever the string is from the last step and add the current character to the left of it. So it'll add E, and then it will add L to the left of what we had before, and then LL, and then O there. So this one, unlike the last one, rather than growing in the direction to the right, where we append things onto the right direction, this grows leftwards, I would say. And so these are both valid ways to do this. They both work. And we can do them with recursion since it is a loop. Anything we can do with a loop, we can do with recursion. So let's quickly try to write this recursively. So we'll just say, actually, we don't even need to write it here. I already have the thing pulled up. So if we print backwards, it's going to have a string and then the current index that we were using, so like I in our for loop that we're using to count through this. And so one way we could do this is we could do the first way where we start at the index equals size minus 1, which is this version. And then we could kind of like work our way backwards. So if that was the case, we would take whatever our string is. I'm not going to use any sort of variable. I'm just going to return straight up. And we could say we want to return string sub index plus our recursive call using the string and the index minus 1. So what this says is take the current character and on the right side of it, and try to build going rightwards using the next number that's back one index. It's at index minus 1. So if we were starting it at the letter O with our index, then it would go to the index where the letter L was at for the next one, and then append that to the right. And so that should hopefully work. This one will build in the right direction. So you can notice the function call is on the right here, which is where this approach, where we went backwards with the indices, that's on the right side as well. And then the other way we could approach this is we could attempt to start counting at 0. And then in that case, we would take whatever the index is, we would add 1 to it to get the next character. And then we would need to append the rest of our stuff, our current character, to the end of what that thing is. So you see the function call for this one is on the left-hand side, whereas the right one is the character. Okay, so recursively, what this one says is take the current character and add it to the string that we would get if we were to reverse the rest of the string from position index plus 1 onwards. So this in a similar fashion to what we had, wherever it is. Oh, it must be back here. We had some stuff over here. I'll get there eventually. We had the letter H, and it just kind of it took that string and then appended this to one side of it. So we could say that this is essentially H. Our final version here is going to be H, with the string containing the rest of the word being LO without the H, backwards to the left-hand side of it, which is what this is, right? It's H with the rest of the string reversed to the left of it. And we can apply that reasoning to any of these. So I could say that the goal after this point is to get the string to the right of HE in the word hello, LLO, and reverse that and put it to the left of this EH string. And that's really what our thing is saying here, is get the string backwards and put it to the left of what we currently have, which is whatever the current character is. And so if I call this really quick, we'll just say hello reversed. So we'll say print backwards, head version, we'll just do the word hello. And this one's at index 0, which I'll do explicitly so we can see. And then I'm going to do the other one, which is the print backwards tail version, which needs to start at the end of the string and work its way towards the front. And so that would be the length of hello, which is, I'm going to do it this way if it'll let me. It won't. Let me just do a constant string word equals hello. And I do need to do one extra thing. I got ahead of myself. What I'm missing is a base case, so this is going to run forever and eventually Stack Overflow. So what we need to check in our recursive cases is essentially whatever it is that would have broke the for loop when we did these things. So if this one is adding one to the index every single time, then we'll want it to stop whenever we hit the length of the string. So we'll say if index equals the string dot length, then we'll just return an empty string because we don't want to do anything more. We'll just return something that has no meaning to it. Again, the reverse is you want to create something in your base case where the problem you're trying to solve is trivial. So whereas the last one was find an element in the array to the right of this, and we had a base case where the array was nothing because that's trivial. If you try to search for something out of nothing, you're going to find nothing, and so it's always false. In this case, we're saying if we try to reverse a string that doesn't exist, then that string reversed is just still nothing, so we can return nothing because you can't really do anything to reverse a string that contains nothing. Okay, so for this one, it would be if index equals -1. We'll say less than 0, just to be safe. Then we'll again do the same thing. Just return an empty string. So if we run that, we should see that I forgot to put an end line again, but both of them print hello backwards. And the point I was trying to get at here is the fact that there's two different ways that you can do recursion, potentially, for certain problems, and they can both be equally valid. They can both get you the same correct result, which is what both of these do. So if I start at the end of the string and work my way backwards, that's fine. And if I start at the start of the string and work my way forwards and then just reverse the rest of the string as I go, then that's all right too. So let me throw an end line before I forget. And so there are two names for these, and you can probably guess what they are because I put it in the function name. Yeah, so I get a question, is either more efficient or better than the other? Not particularly. Yeah, I would say no. I kind of prefer doing the one, this one, because of the fact that you can give a default parameter. This one I couldn't because it has to be lengthened, so that's not something you can know ahead of time because it's not a constant. I kind of prefer the first one because of the fact that you can do that default parameter and then it just makes it easier for whoever's calling your function. But as far as efficiency, there is no benefit to one or the other. But there is some difference in execution, potentially. So that's important. But for the sake of our problem, both are totally fine. They're both okay and run in exactly the same amount of steps. But what does matter, and I'll try to make it super quick because I know we're running out of time. I do have another page. Okay, that's good. Is the order in which the functions are called. It doesn't really matter here, but it could matter if we had more complex things. So for one of these, we had string plus the function call. I'm just going to call it rev, so I don't have to write out all that stuff. And then whatever parameters. And then the other one we had was string sub I. Other way around would be the function call for the head version plus string sub I. So one, the recursion was on the left side of our expression, and one, it was on the right side of our expression. So the first one, this is called tail recursion because the recursive call is on the right side. That's considered to be the tail, and the first part is considered to be the head. And then the other one would be considered head recursion because the recursion comes before the rest of the stuff. And the key difference here, which I'm not going to draw out in full, but we could think about it, is that this is going to create that tree like we did with the factorial, where it then evaluates this to string sub I plus 1 for the tail version. I think that was right. I think it was plus 1. You can correct me if I'm wrong. It might have been the -1 plus the rev for the next call, and then that will evaluate to string sub I plus 2 plus the reverse, and that will keep going until eventually it hits a point where it returns the empty string, which is like the base of our tree. The key here is the order in which the call occurs. So this one is going to expand out to the right as we do this tree, and if I was to draw out this other one, it's going to expand out to the left as I do the tree. And that seems kind of trivial because they're both going to do the same, I mean not the same function calls, but function calls that do the same thing effectively. And so it doesn't seem like it's a big deal, but we have to consider the fact that when you're evaluating expressions in any programming language or any major programming language, that they evaluate in order of precedence first, like the order of operations, and then they evaluate left to right. So when I do this, this will evaluate whatever the local is, figure out what the string is, and then do the function call afterwards, and this one will do the function call before anything happens to that. In this case, that doesn't really matter, but if you have something that you're applying to your recursion that might depend on further recursive calls, then maybe tail recursion is potentially safer, or maybe head recursion is needed if you need those updates to happen later and reflect back on what it is that you're doing. So the key difference, the main thing to keep in mind when doing head versus tail recursion is the order that the function call happens. One happens before the full thing, or before the first part is evaluated, like the other argument, and the other one happens afterwards. So that can occasionally matter. Not so much here, but in other cases. Okay, cool. We finished with just the right amount of time. Does anybody have any last questions before we go? So question, why does isElement work in main even though there isn't a value for the index? Oh, there is. I put it as a default parameter. Do you mean this one? I probably just didn't scroll up all the way. If you put a default parameter like this, C++ makes you put it in a prototype. I don't know why. Only in the prototype, nowhere else. I don't know why it doesn't like it when you put anywhere else, but it'll just fill in 0. if you call the function that way. Yeah, so it does actually know where to start. And that is something that is a little tricky about recursion and writing recursion in such a way that people can easily use your code is you do usually need them to provide a starting point for the function in order to start the call because it needs to know like where you're starting at, which isn't something that the loop normally has to do. So I think usage wise, occasionally recursive functions are a little bit clunky. You can make it nicer if you write multiple functions, and we can talk about that if you want, but yeah, um, you just kind of have to provide it a starting point. Cool. Any other last questions? All right, cool. I will stick around a bit if anybody does have any questions. I'll try to clean up this code and put some more comments on it, and I will see you guys on Thursday.